I will begin, I suppose. It's a go time. All right, I hate to interrupt everyone's social time, but it is time for class. There's the attendance sheet. Let me begin with a word of prayer. So, Dear Heavenly Father, we thank you for this day. Thank you for this class. Again, I thank you for these students. Just ask you just bless our work today. Help us to glorify you in what we do, and just to settle any questions that remain, Lord, about Calculus 3 at the moment, Lord. In your name I pray, Lord Jesus. Amen. So do you guys have any particular questions? Uh-huh.
The second part of 55 about I don't understand that.
The second part of
55.
Let me steal it from you for a second. So, for problem 55, what I would advise all right, suppose you had x to the 17th plus 3 x squared yz plus z to the power 20 equal to 42. All right. And I was to try to answer this question. I think the smart way to answer this question is to take the total differential of the equation that you're given and then use that to calculate partial derivatives. Like the other way would be to calculate, like, okay, let me just do one for instance. So suppose I want to calculate like partial x, rather partial z, partial x holding y fixed, all right? I could calculate this by just taking the partial derivative of this with respect to that rule, right? What would that give me? Well, I'd get, so in this world, the main thing you got to remember is that partial y, partial x is equal to 0, right? That's pretty much it. And so if I take the partial derivative of this equation with respect to x holding y fixed, I'd get 17 x to the 16th dx. Oh, my bad. I can't remember to follow my own instructions here for a second. So again, what I'm doing right now is not the best way, okay? But here's just take the partial derivative of this, okay? So then we get what? We get 17 x to the 16th. And then I'd have what? Plus 6x yz plus 3x squared. Now, y is a constant, right? So in principle, there's a triple product rule here, right? But since partial y, partial x is 0, I just get partial z, partial x, all right? Again, I'm holding y fixed at the moment. And then plus what? Plus 20, z to the 19, chain rule, partial z, partial x, holding y fixed. And then, okay, I'm differentiating both sides of the equation with respect to x, holding y fixed. So the derivative of 42 is, well, 0, all right? And then after I'd done that, what would I do? Well, then I can solve for what I'm after, which is this, yeah? And so I do that. I get partial z, partial x holding y fixed, times 3x squared plus 20z to the 19, all right? That's equal to minus 17x to the 16 minus 6xyz, if I haven't made a mistake. I don't think so. And then I finally, and so after all of this, what have I done? I have solved for what? One partial derivative, right? And it wasn't hard, let's say, not really that hard, but can we do better? And I think we can. Like, this is not the best way to calculate, it's a way. But a far more efficient way to calculate is what I'm about to do in, let's say, purple, if I can find a working purple marker. So what you do is you just take the equation that you're given and take the total differential. So the total differential of this is 17 x to the 16th dx plus 6xyz dx plus 3x squared z dy plus 3x squared y dz plus 20 z to the 19th dz equals to 0. And you see this one equation right here, I can get everything that I want from this. Let me just clean it up just a bit more. So what we should do is we should collect like terms, right? Like this guy, okay, those two. So I've got 17x to the 16 plus 6xyz, that times dx, right? Plus 3x squared z dy. And then my dz's, I've got two dz terms, right? So I've got 3x squared y plus 20 z to the 19 dz. And that's equal to 0, right? See, so once I have that, I can figure out partial derivatives by just solving for whichever differential I'm going to have associated with the dependent variable. So like if I want to calculate partial derivatives with respect to z, I solve for dz. dz is equal to what? Well, dz is equal to minus 3x squared z dy minus parentheses 17. You guys have to help me out if I read it wrong. Plus 6xyz. All right. On all that mess is divided by what? Well, let me try it. Divided by, the first term is divided by the coefficient of dz, which was 3x squared y plus 20 z to the 19. So that gets all multiplied by my dy. And then I've got this same denominator. All right. But you see, I could also solve this for like dy, right? What would dy be equal to? So like isolate dy, right? So I get minus parentheses 17 x to the 16 power plus 6xyz. All right, and that's got my dx on it. And then minus, what's my dz? There it is, 3x squared y plus 20 z to the 19. All right, and that's got my dz. I've solved for my dy. To finish the job here, what do I need? I divide by the coefficient of dy, which was what? Oh, just 3x squared z, right? And then finally, let's solve for dx. If I solve for dx, I get minus 3x squared z dy divided by, what was the coefficient of dx here? 17 x to the 16 plus 6xyz. And that's my, where was I? dy. And then my dz is minus parentheses 3x squared y plus 20 z to the 19 divided by 17 x to the 16 plus 6xyz d, what was it? dz. All right. So, a lot of writing, but what I did here was very simple. All I did, to recap so far, is take the total differential of the defining equation and then solve for the differential, each differential separately. These expressions immediately tell us what the partial derivatives are in all possible scenarios. Like, so let me just start telling you, like this one right here, what is this? This is partial z, partial y, holding x fixed. This guy right here, with the minus included, is partial z, partial x, holding y fixed. So think about it this way. If you want to calculate partial z, partial y, holding x fixed, you put dx equals to 0. And in this case, the partial derivative is just literally dz dx. Excuse me, dz dy. So like if you just solve for dz dy, you get that. This is literally dz dy holding x fixed, holding dx equal to 0. That's the definition of it, actually, right? If we think about dx being like a little increment. Now, you can fuss at me that, there's a limiting process involved, and you're not wrong, but intuition isn't wrong here. So this one is partial y, partial x, holding z fixed. See, because if I set dz equals to 0, dy dx is the partial derivative here. And this one, again, including the minus, is partial y, partial z, holding x fixed. Because if I put dx equal to 0, that's holding x fixed. And then dy dz is literally this quotient. And I think by now you know what this is. This is partial what? If we put this dz to be 0, we solve for dx dy. That's partial x, partial y, holding z fixed. And finally this one, partial x, partial z, holding y fixed. So in order to make sense of problem 55, you have to think about these kinds of partial derivatives. Does that make sense?
How do you see the view from the second half? How do you view z locally as a graph of a function? That's the part I don't understand.
Well, the answer to that question is linked exactly to this calculation. When can you meaningfully solve for dx, dy, or dz? So like the implicit function theorem, what it says is that you can solve for one of the variables, all right, if the partial derivative with respect to that variable is non-zero. Now you're like, wait, you got like 30 partial derivatives on the board. What are you talking about, right? So what I'm talking about is take a step back to the world where they're all independent, all right, the starting point. You have f of x, y, z equals to, in my case, 42, all right? The theorem is that you can solve for one of the variables as a function of the others if the partial derivative with respect to that variable is non-zero at the point and the function's like continuously differentiable. So like if partial f, partial z at a point is not equal to 0, then there exists, like, let's say G, a mapping from, say, R2 to R, I guess, such that f of x, comma, y, comma, g of x, y is equal to 42, for instance. This is the implicit function theorem. Like, it's in my notes, but it's easy enough to miss. And I'm not sure my notes have it stated in quite this generality. So it's a good question you're asking. But like, look at this. Like, so do you understand what I'm saying? This, if you can solve for z as equal to g of x, y, that means that the level surface is a graph at such a point. Does that make sense? When can you actually, so think about what that means to this calculation up here. What is partial f, partial z? What is that? That's exactly, think about it, it's exactly this guy. See that? That right there is the partial f, partial z. This right here is fz. This right here is the f sub y. This right here is the f sub x. And of course, admittedly, if you adopt that level of notation, this problem becomes easier to show that the product of the partials is -1, right? Like if you show the product of the partials is -1 using the notation fx, fy, and fz, it becomes stupid. And all such problems are the same. But it actually looks a little bit more interesting if you look at the product of these functions, right? So to answer your question, Emily, like the answer is in the calculation. The denominator, where that's 0, is where the calculation fails. It's exactly like it should be. Like if you just didn't know any theorems of advanced calculus and you're just asked on the basis of intuition alone, where do these calculation fails? What should we say? I mean, we should say where there's division by 0, right? That has been the case in math up to this point. Of course, there's a bunch of analysis that we're not going to do in here that actually supports my claim there. But other questions? Sorry, I took my time answering your question, but I wanted to show this calculation because while this is fine and you can get by on this, right? You can get by on what I did here at the start. You can get by on this. That is, you know, with fairly little effort, I have all 6 possible partial derivatives for this problem calculated. It would have taken me much longer to calculate it in the way I did the, I don't know, maybe it would take you less time. I don't know. But every one of these that you solve, you still have to like solve for the partial derivative you're after. So any way you slice it, you're doing algebra here. Why is that? Because the defining equation implicitly defines x, y, and z as functions of one another, right? This is sort of an analog of the implicit differentiation problems that we had in Calculus 1. Other questions? Sorry, I don't have your quiz graded yet, guys. I haven't lost it or anything. I've been super busy this week, and I keep falling asleep, which doesn't help. So, so no other questions? So are the harder problems at the end of my homework in the solutions to the old years? Is that what's?
No, there's examples in the end of chapter problems.
Ah.
They're not like exactly like the other way.
Just close enough that.
Yeah,
I see.
follow it. Like this one, it had it done that way.
Oh, okay, okay, good.
But it wasn't like a problem. It was just like the one.
Mm-hmm. You said problem
60.
Thank you. So here we have total differential. We got a function of 4 variables, right? Take the total differential of that. And then the question is, what 6 conditions do we need in order to find out if something's an exact equation? Now, I threw out that terminology exact like last class, right? So let me talk about it. So the quick answer to the question is it's all about the partial derivatives commuting. That is exactly everything here. Like all of the things failing to be exact, that differential failing to be the total derivative of something else. It is all about the partial derivatives not commuting. If that happens, then you can't find the function which differentiates to give the whole thing. So let me do an example. I guess it's example 1. I don't know, 2 maybe. So let's say, suppose you had like, I'll make this really easy. Let's see here. Well, easy but not trivial. Easy but not trivial. So let's see here. X, y, z plus t dt plus t, y, z plus x squared dx plus t xz plus, I'll give us a y cubed dy plus, oh, I don't know, t xy plus z to the power 4 dz, all right? And suppose that's all equal to 0. So you're given, this would be kind of analogous to the one that's in that, right? So, so to say that that's an exact form, what that means, this would be an exact form. Exact means there exists f of x, y, z. Well, I'm using t first here. So t, x, y, z, such that df equals to 0 is exactly the same as that. In other words, the expression with differentials is exactly the total differential of one function of x, y, z, and t, x, y, and z. So let me just tell you what the answer is here. Now, how could you find it? You can go through that integration procedure like we did for the two-dimensional problem, like do an integration of this with respect to t, and then you plug that into the next one, integrate with respect to x, plug it into the next one, integrate with respect to y, plug it in the last one, integrate with respect to z. But what I like to do is to just think about integrating each one separately and just sort of adding the answers together and then adjusting my answer to remove any redundancies. Basically, I guess and check. That's the better way to do these. It's less rigorous, right? But in terms of actually finding the potential, I think that's the way to do it. So like this one, can you guys tell me what I put down? What would be my answer here? In terms of, this actually is exact, I think. What's my so-called, this is, by the way, the so-called potential form. Well, potential function, I suppose, here. So, what's that?
X, Y, Z, t plus 1/2 t squared.
Right, t, x, y, z. That's a very good thing to write down. What does that immediately get me? So remember that by definition, this here is ft dt plus fy, fx dx plus fy dy plus fz dz, right? That's the total differential for 4 variables, right? So Shane is right. If I put this down, I automatically generate what? This guy, this guy, this guy, and that guy. Partial differentiating this with respect to t, with respect to x, with respect to y, with respect to z, respective. So that gets those things. But how about the other? I think you told me one of them. What'd you say?
1/2 t squared.
Plus 1/2 t squared. Now that is just what you got from integrating this with respect to t, right? But if we did this one, we pick up a 1/3 x cubed. This picks up a 1/4 y to the 4th, and I regret my choices. Plus, fine, I'll do it like there. And my apologies about the double plus again. I still haven't learned. 1/5 z to the 5th. And so there you go. That's the potential function here. So here's some. So to think about this, the only way, the reason this was possible, if if it wasn't possible, if you integrated one way or another way, you'd get like a different answer. You'd come to inconsistencies plugging one equation into the next after the integration. But like let's look at this. So you have, so that's how to find the potential if it actually is. This one here, though, let's think about this. So the question is this equal to df, right? I mean, this is equal to df, okay? What I wrote is literally df by definition. The question is, you know, if I have something else, let me just use different letters like a dt plus b dx plus c dy plus big D dz. Like, what conditions are necessary on A, B, C, D in order for this to like work? I talked about this when we just have two, right? Remember? If we had like omega was say p dx plus q dy, if that's equal to say big DG, which is gx dx plus gy dy, right? What did that force on P and Q? Do you remember this? This actually matters more because this actually comes up in other things more so. We don't do too much four-dimensional stuff in other courses, but this comes up. So in order for this gives me what? P is gx, right? And Q is gy. So you see partial y of P is equal to gxy, but that's also equal to partial x of Q. So I need that partial xq is equal to partial yp because partial derivatives commute. So that's what we already know. And we're trying to generalize that now to this context. I said there are 6 conditions that you're looking for. What are they? Let's pick on these two guys, right? This and this would ostensibly be that and that, right? So we have, on the one hand, A is equal to ft, and B is equal to partial derivative of f with respect to x, right? These aren't necessarily linked because partial derivatives commute. What's the equation we have relating them? See, I have to have that partial x of A, which is actually going to be f like tx, right? But that's equal to partial t of B. Does that make sense? Because the partial derivatives have to commute. So if they're both coming from the same function differentiated, then we're forced to deal with these issues. And if you can play that game with A with respect to B, you can also play it with A with respect to C and A with respect to D. You get the relation of partial derivatives, like the t and x derivatives, the t and y derivatives, the t and z derivatives. They have to commute for the opposite things. Yeah.
Could you generalize that request for information by saying partial x, y, z of t is equal to partial t, y, z of x is equal to partial t, x, z of y is equal to partial t, x, y of z. So do triple partials on each one and something like that. Would that still be?
Well, but we can get hung up. I mean, oh, you're like, well, what about the higher partial derivatives? Well, the thing is, I'm just looking for something to spoil it, right? So if I can get into trouble with the second order partial derivatives, then I'm content with that. But you're right. There are also necessary relations between the triple partial derivatives of these things and the quadruple. In fact, generally speaking, that's a very interesting question to ask. Given a differential equation, what is the collection of all its differential consequences? And how would you make a mathematical object to capture that idea?
Could you equivocate that if they're triple, if they're doubles are equal?
I don't think you're wrong. I'm just saying, like, I'm just looking for this problem, I'm just looking for like first, so these aren't even second order. What I'm trying to say is here, these was based on the second order partial derivatives of the potential function commuting, but it actually has given us first order conditions on the given coefficient functions for the problem. So like, just to be more concrete here, if I had something like, you know, x dt minus t dx plus y squared dy plus, you know, y dz, this would not be exact because if this is right? If this right here is partial f, partial x is equal to x, right? My bad, t, right? Partial f, partial t would be x here. And this would say that what? Partial f, partial x is minus t. So if I differentiate this with respect to x, I get what? 1. Whereas on the other hand, this one over here, if I do the mixed partial, I get minus 1. Game over. It's not exact. Failure in one of these conditions is enough to strike it down. It doesn't have to fail on all of them. I don't know if I've answered your question or not. It's too early. I'm sorry. That thing I was talking about, like the differential consequence of the differential equation, is like an area of active research. People have been only thinking about this idea for maybe like the last 40 years or so. There's something called an exterior differential system, which formalizes these things. And it's this sort of like complicated amalgam of abstract algebra and analysis. It's heady stuff. I don't entirely understand it. I tried for a while. I understood something about it, but there's not a good introductory book in it as far as I can cipher. Other questions? Yeah. 58. Thank you, Emily. I do have my own, I promise. Okay, so here, you really just need to follow what the hint is and literally replace the double derivatives with x and y with like the double derivatives with respect to u and v. So let me get you started on this one, if I can. Am I safe to erase here? Okay. There is, full disclaimer, a more beautiful way to capture all 6 of these relations in terms of a systematic operation that you can do on differential forms called the exterior derivative. At the very end of the course, I'll talk a little bit about that. It's not part of the required material or anything, but it is really cool. Unfortunately, it just doesn't exist in any of the standard curriculum. So, so we're trying to convert Laplace's equation, this guy, right, into the like a u and v PDE, right? So PDE means partial differential equation. What is a partial differential equation? It is an equation, get ready? It's really difficult, that involves partial derivatives. Okay. Do you know what a differential equation is? Okay. An equation, yeah, an equation that involves, well, differentials, yeah, but we usually say derivatives, but yes, yeah. That would be a very good answer for my course at the moment, the way I've been talking about it, because I've been very much taking the differential viewpoint in here. There is more to say about that, by the way. I can show you something really neat if we have time. We have time, cool. But let's finish this problem first. So, what, you guys tell me, what was the definition of the u and the v? I forgot.
U is 3x plus 2y.
Okay.
V is x plus y.
X plus y, okay, great. And we were going to figure out, like, what is partial x? We want to convert that to u and v derivatives. So, like, partial x would be partial u partial x partial u plus partial v partial x partial v. See, that's the chain rule that's of interest here. Now, in order to calculate those, I would need to have solved for u and v as functions of x and y. Woohoo! We already have that. All right, so there's nothing to solve here. See, a more annoying way to tell you this problem would have been to give you x and y as functions of u and v. Then you'd have to, like, solve those for the other way around or something. But anyway, we didn't do that. So we can calculate these partial derivatives, and what we got. Partial u partial x is 3, right? Partial v partial x is 1. Likewise, what's partial y? Well, partial u partial y, partial u, plus partial u partial, partial v, partial y, partial v. So I'm just writing the chain rule without a function, if that is okay with you guys. I'm looking at the chain rule as a rule for defining operators. So an operator is a function of functions. It's something that would apply no matter what function I hit it with. But anyway, so what are those? 2, right? And how about this one? 1 again, right? Now all I have to do, it's very simple, is I come up here, for example, Vxx, what is that? Well, that's partial x, right? Partial x of phi, right? So I just trade out my partial x derivative for these guys. So I've got 3 partial u. I'm getting really tired of that notation. I'm going to flip over to the much easier to write partial u plus partial v, if that's okay with you guys. And then we've got like 3 partial u acting on phi plus partial v acting on phi. Are you guys tracking me so far? Okay, so then what? Well, these are partial derivatives, right? So how does that work? You partial differentiate, right? We have linearity, right? We can pull constants out. Beware. Well, we started working a problem like this. I worked about half of the problem like this with the polar coordinate Laplacian, right? That was much uglier because there's that 1 over r term in the derivative that appears because of the angular coordinate being different, and then you end up differentiating that. Like you end up with derivatives of products of functions in the double x derivative, but not here because these are just linear in the sense that they're just constant multiples. They're like, there's no functions of u and v appearing here, right? So it's not hard, it's just work it out. I mean, this is literally 9 partial u phi plus, let's see here, 3 partial u partial v phi plus partial v of 3 partial u phi plus partial v. See, constant coefficient partial derivatives behave just like polynomials. The algebra here is really simple. And because they commute, right? Those commute. So what can I do there? I can group these guys together, and really what I have here, if you don't mind me switching over back to the other notation, is I've got 9 phi uu plus 6 phi uv plus phi vv. Now that's half the homework problem I did for you. Can you do the other half? Do you see what needs to be done now to finish it? Yeah. So it's interesting, right? Like, it looks to me, I don't think there's any cancellation. So I think when we change from xy coordinates to these uv coordinates, we pick up a mixed derivative term in the Laplace equation. So there's an important lesson to learn here, is that if you take a differential equation that's written in one coordinate system and you change to a different coordinate system, the differential equation does not have to have the same form. Generally speaking, it will get modified. If you can find common systems of coordinates that when you change coordinates, the equation has the same form, that's special. Beautiful. Nice. But not the case here. So I've given you something ugly. Any other questions?
Would you use this to translate geometry or something?
Translate what?
Would you use it to translate geometry from one to another?
Something like that. Like, you know, I mean, these kind of equations, it would be something like, you're like tilting your axes and putting things on a slant. You know, they're no longer perpendicular. There's sort of like slant coordinate lines. So there might be a good applied reason for looking at coordinates with respect to that because of like how your data is collected or something. You know, like maybe your situation you're in physically, you just don't have like a sensor system which is set up orthogonally. Maybe it's set up on like slanted lines, and then this would be the more natural coordinate system to solve things in. As a general rule of order, if you do numerical methods on a problem where the coordinates are directly resembling like data that you have, you get better results. A particularly like weird example of this is I had a friend who was working, and this is probably classified, so, but it's like pretty old, so it's probably okay. But it used to be that the subs, their like navigation underwater would be based on the Earth being a sphere. And so after a few months, you know, two of these subs tried to go meet each other underwater, a mile underwater or whatever, however far they are, I don't know. Appropriate depth, I don't know, whatever. And then they'd be off by like 100 meters or something, right? So this is kind of bad because what that means is that the software, which is calculating where they are as they're underwater and don't have a way to like recalibrate it, it's accumulating errors over time, and it builds up, and eventually they can kind of see, oh man, we're really off. So what my friend did was to rewrite the software so that it was instead modeled on the Earth being an oblate spheroid. So the Earth is not in fact a sphere. It's squashed a bit like this because it spins at the equator. I'm sorry if you're a flat earther, I can't help you. But so it's squished at the equator a little bit, and so it's like the geometry which more closely models the Earth is the oblate spheroid geometry. And so when you do your navigational calculations in that bigger frame of things, you get better numerical results. So anyway, that's the kind of reason that sometimes we have for changing coordinates. But honestly here, to be totally honest with you, it's practice for the chain rule. I mean, I'm sorry it's not too exciting, but it's like the honest answer. Whenever any of you ask me, well, where am I going to use this in the real world? My inevitable response to you will be that you should believe in your own existence, right? Because you're in the real world and you're taking my test. So, just saying. This, of course, is not the answer people are looking for. But the truth of the matter is if you give the people the answers that they say they're looking for, they complain. Because I've put applications in courses before that are more real, and you know what happens? It is not welcomed. Even my silly ninja problems are annoying to you guys, right? Right? I mean, maybe. I don't know. Listen, there's something else we can do with differentials that's really, really neat. And maybe this is also a helpful thing to talk about. To understand vector fields better, because this is how we have to understand them in physics. So in physics 2, like when you take physics 232, if you do, some of you will, we talk about the concept of a flow line or a streamline to a vector field, right? So like, for example, quintessential example, if you've got a charge at the origin, right? Electric field lines flow out of that, like this. And so, actually, the way we do this in physics is that field lines only begin at charge, and the density of field lines is an indication of magnitude. And we draw little arrows on them like this to indicate the direction of the vector field. So these are called field lines. And so what's the electric field actually look like? Well, if I'm so foolish as to try to graph it, the Coulomb field, right? The Coulomb field, actually the formula for it is this. It's 1 over 4 pi epsilon naught. There's a Q up here, and then you got yourself a rho hat over rho squared. And there's a minus. Nope, there's no minus. What am I talking about? It's outward. If the positive charge, then your electric field lines are pointing out of the origin spherically in all directions. The magnitude drops off as the reciprocal of the distance from the origin. And if the charge is negative, then the field lines point into the origin, right? Positive charges are a source, negative charges are a sink. And so like the electric field, if I was to pick a point, right, it looks like this, okay? So you see what's going on here. Here's some sample electric field lines, electric field vectors. So can you guys tell me, if these are the electric field vectors, and I'm not doing a very good job drawing their magnitude, right? In fact, I'm doing it opposite. The electric field, how big is the electric field at the origin? It's pretty big, right? Yeah, it blows up. It's infinite. Of course, there are electric fields everywhere, right? There's everywhere. But you notice that that was supposed to be out from the origin. My bad. Can you describe to me geometrically what's the relation between the field lines that physicists like to look at and the vector field that we're given? What's the relation between the field lines? The geometry of the field lines and the vector field, what is it? Let me tell you what it is. If we have a vector field f, right, and we evaluate it on a curve, let's say gamma of t, right, if that's equal to d gamma dt, this makes it a so-called integral curve of the vector field f. In other words, it's a curve that when you evaluate the vector field on the curve, the tangent field to the curve lines up with the vector field. So let me give you an example of this more explicitly. And I'll make it two-dimensional because, you know, I'm not sure what example I'm on. Let's call it 4. I don't really know. I like this vector field. F equals to, let us say, minus y comma x. So let's try to find integral curves of this. Let's see what we're up against if we try to do that. So we're looking for gamma of t. Let's let that be x of t, y of t for the sake of like nice notation. So if you look at f of gamma of t equals to d gamma dt in the xy notation, this is interchangeable simply with what? So d gamma dt is nothing more than the velocity. It's dx dt dy dt, right? So what we got here is minus yx equal to dx dt dy dt. And in this context, x and y are functions that we want to find. All right? So what do you have to do to find the x and the y here? What do you have to solve? Now, properly speaking, this problem belongs to differential equations, but the thing is we never cover it in differential equations, so I'm covering it here. So like, I have to solve dx dt equals to minus y, and I have to solve dy dt, right, equals to x. If I solve it directly, that's what I have to solve. Now we can solve this directly. There's a strategy for doing that, which after you have differential equations, it's really reasonable. Because to solve it directly, all you do is you take, like, say this one, right? And you plug it into that one. And what you get then is what? You get d squared y dt squared is equal to minus y. And if you had my calculus 2, you've worked this out. You worked out the solution to this differential equation already. You learned that the general solution to the differential equation y prime prime plus y equals to 0, you learned that the general solution to that, in fact, is y is equal to like c1 cos t plus c2 sine t. Or if you like, we could just write it as y is equal to some constant r times the sine of t plus some phase angle. All right. On the flip side, once I have that, I can calculate x, see, because x is equal to dy dt, which is equal to, if I differentiate this, r cosine of t plus phi1. I prefer, let me erase this from the record. I mean, this is true, but not helpful to us at the moment. Okay, so I'm going to erase this. That's the standard solution you learn in Math 334, okay? But these are nice because you guys can tell me what's the geometry of the curve. What are we looking at? That's the parameterization of some curve. What is it?
A circle.
That's a circle. Does this make sense? Well, let's plot the vector field for a second. This is always a dangerous vector field to plot. Let me pick 4 points. All right, so what is, you guys tell me, what is f of 0, 1? If I plug in f of 0, 1, what do I get?
Negative 1, 0.
All right, so that's, oh, I'm a dummy. F of 0, 1 is where? It's up here, right? So negative 1, 0 would be like this, right? And what happens when I plug in f of 0, 1? Oh, I already did that. I'm a dummy. I'm sorry. Hold on a second. I'm having trouble. Okay, f of 1, 0 is what I want next. What's f of 1, 0? So I get 0, 1, right? Wait a minute, I'm a dummy. Like, good grief, look at that. I can't plot a stupid arrow. Seriously, like, look at this. Which way does minus 1, 0 point? Is it this? No. Good gracious. Now, 0, 1 is like this. What happens with f of minus 1, 0? Zero minus 1? Is that right? Yeah? So 0, so that's like this. I better stop. Yeah. Sorry about that. These things happen. But it's a really cool vector field. It's not my fault. Stupid Germans. Let's see here. So, but here, if we add more, then it's okay, right? And then, oh, I should add some diagonal ones, right? Because there's also these guys, right? There. Now we're okay. Anyway, so if I could do this better, there's ones here, and there's ones over here like this. There's ones over here like this. There's one like this. There's ones like this. I mean, I'm not doing the... You can see that this vector field is encircling the origin, right? And in fact, the streamlines to it, we just calculated through things you don't know, admittedly, that the field lines are like this. But I want to show you how we can... So this right here is kind of pesky, right? In terms of things you know. This is a little bit pesky because this is what? This is a system of differential equations, right? Can we trade this for a differential equation in the sense of calculus 2? We can. Let me show you how. Check this out. So what should dy dx be equal to? Shouldn't it be dy dt over dx dt? Because after all, what am I doing? I'm just dividing by dt, the top and bottom, yes? But what is dy dt and dx dt? Oh, well, we know what we want. We want x, and we want minus y. Oh, look at that. So now, what are we up against? We're up against minus y dy equals to x dx, or better yet, x dx plus y dy equals to 0. But you guys can easily see that that's an exact form, and that we can integrate it. And the integral of this is exactly, well, it's the differential of 1/2 x squared plus 1/2 y squared, see, equal to 0. In other words, you can see that x squared plus y squared equals to r squared is the solution to this differential equation. So anytime your differential equation, anytime you have like a system of differential equations where the functions that appear over here are just involving x and y and don't involve time, you can do this trick. You can eliminate time by just dividing the derivatives like that and solve the corresponding equation in x and y. What happens is you'll find the level function, right? You'll find a level function, and the level curves to this will actually be parameterized by the solutions to the original problem that you're looking at. If you're just interested in the geometry and not the specific solutions as a function of time, this is a very useful thing, because you can easily solve that kind of problem. So anyway, this is just another example of like heuristic differential calculation, again, being super useful. But there is danger, right? Like Shane pointed out, like the -1, right? Is it -1? Is it 1? So if I gave you guys a similar problem in the math battle, do you think you'd have a shot at it? No? What if I just changed, what if all I did was just remove this minus? No? Oh man.
We could just copy that down and flip the graph upside down.
No, if you remove that minus, it's a totally different problem. Instead of getting y prime prime equals to minus y, you end up with y prime prime equals to plus y. Do you guys see that the solutions to this should be sine and cosine? This shouldn't be like a terribly deep thing. Think about this. If you differentiate sine and cosine twice, what happens?
It becomes negative.
It becomes negative what you start with, right? So yeah, sine t and cosine t are solutions to this.
So it would be an exponential equally hyperbolic.
Right. It's hyperbolic, yeah. It ends up being Cauchys and Cinches if it's just a plus. And Cauchys and Cinches parameterize what? Hyperbolas. Because this calculation over here, once you delete the minus, becomes like, you know, x dx minus y dy equals to 0, which has solutions like x squared minus y squared equals to a constant, which are hyperbolas, either opening vertically or horizontally, depending on whether you choose the constant to be positive or negative. Or if you want to be difficult, you can choose the constant to be 0, and then you get lines that cross through the origin. At the origin is the one place where the level function thing breaks down in terms of its relation to the curves. But okay, anyway, I just want to show you guys this because it kind of slips through the cracks. Like I've started differential equations when I taught it before with exactly this discussion, but it's like not in the book, and I'm like 95% sure I'm the only person who does it. So I think it's interesting. Now you could disagree. Any other questions? Could we come up with a compromise? Like, it could be on the math battle, but it's not on the test. Would that be a suitable middle ground for, we could look at it a little bit, but not too much for that? Bonus credit. So I should, if it was worth, if there were bonus points on the math battle, would that make it? Nah. I'm not playing poker with you guys. But again, that's mostly because I don't know the rules. So. All right, well, let me turn off the camera as we have other business to attend to. Oh, sweet.